Now that we learned track stacking, track summing, and how to prepare or organize our tracks for mixing, let's get into learning few fundamental digital signal processing like filtering, compression, expansion, gate, stereo imaging, surgical compression, parallel compression, etc. etc. For today's video, we would try to cover everything related to filtering. So let me just create a new track, audio track, and put a test generator. Let me reduce the levels within Logic so that it is not annoying to your ears. So we have a test generator which is running a sine wave at 1000 Hz. To check this, we also need to put a filter. I'm going to use a FabFilter Pro Q2. So if I dial in 2000, you could see the filter also shows me the 2000 graph. As I reduce down, you could see whatever the tone is generated is been displayed in this particular analyzer. So let us put it back to 1000 Hz and switch from sine wave to square wave. Now you could see many graphs formed on the analyzer. Let me quickly close down the volume from Logic. So we just look at the graphs and try to understand. I don't want to keep that annoying square wave or sine wave coming in through the speakers. So now you know square wave has got many frequencies, but though the oscillator is producing only 1000 Hz. So these additional frequencies are called as harmonics. For sine wave, there are no harmonics. Hence, we always call sine wave as a pure wave. So we also have triangle wave and sawtooth wave. Both triangle and square wave has odd harmonics. It means if the oscillator or the sound generator is generating say 1000 Hz, you will have 3000, 5000, 7000, 9000 and so on. All these extra frequencies that are seen on the graph are multiples of odd numbers. If you go to a sawtooth wave, you will see both odd and even. So as of now, this particular tone generator is not having a sawtooth wave, but if it has, if maybe I'm enabling it, you will see 1000, 2000, 3000, 4000, 5000. So to put it very simple, sine wave has got no harmonics. Sawtooth wave has got both odd and even harmonics. Square wave and triangle wave both has got only odd harmonics. So let me put back to the sine wave and look into the features of this particular filter. Filtering means removing those frequencies that are not required. So the frequency that is required in this graph is only somewhere around 1 kilohertz. So this area I don't want, so I need to filter it off, and this area I don't want, I need to filter it off. Simply I can click, it creates a series of nodes. As I click one of the node, I could see possible controls for this particular node that is selected. So I have the frequency. So as I dial in the frequency, you could see I will be able to change the position of the nodes from far left to near the particular graph which is displayed on the filter. And then I have an option of how I need to filter it. So as I click here, I have many options. Bell, low shelf, low cut, high shelf, etc. etc. So we know that this is going to be a low cut. Anything lower than this particular graph need to be cut. So I need to select a low cut, and this is a slope. As I increase this decibels per octave, you could see the slope is, there's going to be a power move. So the slope is very abrupt. So we are cutting it right this. If I keep increasing my decibels, you have a gradual cut. So you could see there's a gradual cut forming on the filter. So let me now choose a very steep slope and move it closer to this particular graph displayed. And similarly, I do the same thing here. Choose, this time I'm going to choose a high cut filter. So anything higher displayed on the graph has to be cut. And I want a very steep cut and bring it very close to the graph. So it means I am going to remove if any frequencies that are present below the graph, if any frequencies present above the graph. So I have deployed both low cut filter and a high cut filter. Another way, what I would do is, for instance, let me change this to a square wave. Now you will see square wave has got extra harmonic content, but I had filtered so much, so these frequencies are now removed. I don't want that to happen. So as I see these frequencies popping up the graph, I need to extend this far right so that I am still accommodating all other frequencies that are present within the range. All right. The next thing is, sometimes by moving this point closer to this particular graph, I would still start filtering those sounds that are required. So what I can do is, as I click the node, so let me just put back to sine wave and bring it down like this. So we are working currently with the sine wave. As I click a node, you would see a headphone symbol. When I click this headphone symbol using a mouse, you would hear the sounds that are only filtered. I can start bringing it slowly and also watch this particular meter. So now we have not included any of the sounds that's there with this 1000 Hertz. As I start bringing it closer and closer and closer and closer, you could see there's some meter levels. So it means I'm actually rolling off few of those 1000 Hertz. So required content from the 1000 Hertz are being now rolled off. So I don't want this to happen. See, this tends to be over filtering. So move this to a level that you don't actually see anything above minus 50 on the graph. So this is exactly, this is minus 45, minus 50, minus 55, minus 60. So make sure you don't filter anything above minus 50 or minus 45 always. So let me keep my filter here. Do the same thing for the high frequency. By soloing it, now I don't see anything on the meter. This is your meter. As I bring closer, I can see there's some sound popping up on the graph, and I will take it closer, 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 so that the meter is not exceeding minus 50. So this is a pretty decent level of filtering. Next important thing is, let me select this particular graph and switch it off. Select particular graph and switch it off. Okay. Now, if I select a particular frequency, you always get 3 knobs. So this knob is to dial in the frequency. This knob, for example, I'll click another node. This time let the node be right at 1000 Hertz. I could also key in the 1000 Hertz. So this is exact 1000 Hertz. I can choose to increase or decrease by using the middle knob, which is the gain knob. Now you could see my intention to increase or decrease is only for this 1000 Hertz, but this particular plugin or the equalizer increases all these pink areas. So these areas which are adjoining to the fundamental frequency are called as the bandwidth. I could narrow them or increase them by using the third knob. Now you see this numbers, when I extremely dial down towards my left, the numbers are far lower, and this is going to be higher numbers. As bandwidth and Q are inversely proportional to each other, if the Q values are lower, bandwidth is going to be more. For example, as I dial down, the Q values are in 0.1 point. So these are very lower bandwidth or lower Q numbers, but you could see the bandwidth is more. Now if I increase it to the far right, it's now 15, 31, 40. Now you could see the Q numbers are higher, but the bandwidth is lower. Now you know that I could adjust this, the third knob, to an extent so that the whole of what is displayed in the graph is selected. Now I could increase or decrease whatever I want. I can actually do it. You also have a smart control here. Just click on this node, and if you are using a mouse, by using the scroll, you can control the bandwidth. So you need to know that bandwidth and Q are inversely proportional to each other. Next, if you hold command and try to move this frequency, you'll be only moving the frequency and you cannot increase the maximum level. So this peak is corresponding to 9. Now I'm holding my command key so that I'm not able to decrease it or increase it. I'm actually only changing the bandwidth or the position, but I'm not able to increase or decrease it down. Same way, now I have removed my command key. Now I have removed it. If I hold my command key, I will not be able to further decrease it or increase it, but just keep changing the positions or increasing or decreasing the bandwidth. So this lets you to move to nearest frequencies without increasing the gain of the selected frequency. So as of now, I want to be precisely at 1000 Hertz. So let me dial in 1000 Hertz and choose 1000 Hertz and choose my Q to match to that of what is seen in the graph. All right. Next thing, you have an option called zero latency, linear phase, and natural phase. So this is very important to understand within the plugin. So zero latency means it will not load your computer. So this plugin, when it's kept at zero latency, is not going to load the plugin, but there might be certain phase issues. If I keep it natural phase, it's somewhere between zero latency and to the linear mode. If I choose the linear mode, so this plugin might load your CPU, but there will be very, very minimal phase issues. So whenever you combine few tracks into an aux track and then try to do a batch processing, keep this to be linear phase. Or if you deploy this particular plugin on a master track. So master track is a track where whole instruments are going to come into the master track, and from the master track you are going to listen through your speakers. So whenever you combine many instruments, always use a linear phase so that there are no phase issues, but the CPU is going to get loaded. You also have a MIDI kind of a symbol here. So as I open this, you can see that there's a keyboard mapping that's integrated within the plugin. So if you know that I have played a chord, for example, like C, E, G, or maybe like C, E, and the next octave C, we know as a programmer that these are the fundamental frequencies that's present. So that's going to be C, E and the next octave C. So I can simply click here, this is the C note. So double click the C note, you can see a node is formed. The next note I played is E note. So double click the E note, I can see a next node is formed. Then I played a 1 octave higher C. So I am able to very precisely select the notes that I played on my keyboard. And if you feel that the E note is a bit louder, I can just reduce the E note like this, and we need to have a very narrow bandwidth like this. So the C and the next octave Cs are okay, that doesn't require any reduction. Probably the E note is being hit very loud, so it's kind of an annoying in your headphones or monitors. So I want to just reduce this E note. I can precisely select the notes and move it. So I can also quickly move this like this, put it back to the E note. If maybe F sharp, I can put it to the F sharp note. I can move it on my keyboard. So this lets you to pick the frequencies that are played and fundamentally work on those. Let me reset the graph to factory default so that I don't see any peak. And as we are running through a 1000 Hz sine wave, you can still see a 1000 wave on the graph. The next thing, we'll look into the analyzer. As you see, you have an option here. When I hold the mouse, you have a new dialog popping up. I could see previous to the EQ, the graph, or the graph can be viewed post the EQ, and you can also view the sidechain. These are very powerful features that will help you to fine tune your EQing skills. So let me just take off the pre and the post. You don't see anything on the graph. Still, you'll be able to do an EQ. You'll be able to listen to what you are EQing, but not visually see what is happening. So let me go here and choose pre. So this signal, so for example, I'm doing a boost and I'm reducing the bandwidth, or I'm decreasing the bandwidth, anything. In this mode, you are seeing the graph previous to the equalization. That is, you are directly monitoring the input. Now, if I go and choose post and take off the pre, now you are actually monitoring the signal that is post the equalizer. So as I reduce, you can see the peak becomes lower and lower. So the graph displays the signal that is post, after the equalizer. When I enable pre and post together, now you can see earlier, before equalizing, the graph was so much, and after equalizing, you can see a grayed out area. So this is what is happening after equalization. So this much of signal has been reduced. This helps you to identify the frequencies and how much you have retraced from the existing values.